I've been doing web scale transaction processing between Google and Facebook for more than 11 years. Most of that is with MySQL. And some of that is with RocksDB and MongoDB. I don't have a fancy title. We don't have fancy titles at Facebook, so I am member of technical staff. My project is really making MySQL better. My focus is on storage efficiency. We have a lot of data, so we need to be efficient at managing that data. And I'm really here to explain the case for right-optimized database algorithms via RocksDB, MyRocks, and MongoDB. And so I'm going to explain why we are interested in this, and I don't have many details on how to do it. It's not a tutorial on using these products. Really, it's just making the case, what are the benefits that we see in them. I also don't discuss everything from first principles, so I'll talk about a B tree and a log-structured merge tree, but I won't go into much detail about what they are. So RocksDB, MyRocks, and MongoRocks are the right-optimized database engines that I care about. RocksDB is an embedded key-value storage engine. This was a fork of LevelDB. The code has changed significantly since the fork. I don't think you would consider it a fork at this point. I'm not sure if we integrate changes from them anymore. MyRocks is the RocksDB storage engine for MySQL. We've been working on this for several years. The MySQL storage engine API is extremely hard to implement. Many projects have tried without great success. MyRocks is succeeding. It is running in production today. We are migrating the user database tier, which is the largest transaction processing tier at Facebook, migrating this right now from InnoDB to MyRocks, which means we continue to use MySQL. MyRocks is coming to Percona Server and MariaDB Server. I'm excited about this because I want people outside of Facebook to be able to use MyRocks, and for that to happen, it needs to be in a proper distribution with expert support, documentation, training, so Percona and MariaDB can make that happen. I don't know if he's here. Sergey Petrunia is helping us a lot in terms of implementing MyRocks. He works with MariaDB. MongoRocks is a RocksDB storage engine for RocksDB for MongoDB. The API is much easier to implement, a new MongoDB engine. So in 1 year, this went from idea to running in production. It's available in Percona Server today. And again, the big deal, MyRocks is running in production. The database tier that's being migrated to it is tens of petabytes of storage. So we're excited to potentially compress that in half with MyRocks. RocksDB, MyRocks, and MongoRocks, the goal here is efficient performance. A lot of databases are marketed on performance, and we want to make efficiency as important as performance when judging a database algorithm. The goals here, and we had a lot of discussions early on when trying to understand whether it was worth spending time on this project. The first was, how can we be slower than InnoDB? Can we sacrifice response time or throughput? And it was hard to be specific because I didn't want to kill the project early. So I just said, well, we need good enough performance. We need to be comparable to InnoDB. In some cases, it's going to be okay to have a worse response time or to have less throughput. And so we needed good read efficiency, not necessarily great. But it turns out we're doing better than good. The next goal was, and I think I added this after the fact, was better write efficiency. So we use SSD. For transaction processing, it's very hard to find people willing to put new workloads on disk arrays. When given a choice between using disk and SSD, everyone chooses SSD. So we don't want to worry as much about SSD endurance. Better write efficiency, meaning the same workload writes less to storage per transaction, makes SSD endurance less of an issue. The last is best space efficiency, and this was the number one goal. We had initially decided that we wanted 2x better compression than compressed InnoDB. So we wanted to use half the space compared to compressed InnoDB to make this project worth doing. Migrating tens of petabytes is a hard project. We want a return on that effort. Best space efficiency, best compression means we use less SSD, or the SSD we have in production can handle a growing workload. Something I didn't write on here, and it's a benefit that we see potentially, in addition to using half the storage, potentially we can consolidate the number of servers in half. So we're going to potentially put twice as many users, twice as much logical data per server, if we have enough CPU to make that happen. And for a variety of reasons, I'll explain some of them later, performance is complex. Read efficiency with the LSM tree, in many cases, is better than the B tree with InnoDB. Benchmarking is something I make jokes about. It's a term I'm trying to make popular. Benchmarking means the act of claiming that one product or one database engine is better than another based on performance results that are not explained. So it's really, I'm showing you a graph. Look at the bars that are higher, that product is better. It's sometimes it's good for visibility or getting page views, but there's a lot more to performance that performance requires an explanation. Explained performance is expensive. It takes a lot of time for me to run results and then be able to explain them to myself and to other people. Here, Myrox is competitive with InnoDB. I was surprised. This is a in-memory, very small database, very simple workload, not ideal for Myrox, but early-stage Myrox is competitive with InnoDB. So I'm doing some benchmarking because I market Myrox. But something is better for reasons beyond more throughput or better response time. I'm hoping that people who publish performance results, in addition to providing throughput or response time, also provide metrics on quality of service. What's the 99th percentile response time? What's the worst case throughput? Because stalls in performance are really bad for end users. The other one is efficiency. QPS, or transactions or queries per second, tells you how fast you're going, but you want to know how much hardware you are consuming to go that fast. So here, this was a TPCC MySQL workload. It's I/O bound. The server has 50 gigabytes of memory. There's 1,000 warehouses. The database is much larger than memory. The first metric is throughput. Myrox wasn't designed for this workload, but it turns out to slightly exceed uncompressed InnoDB on throughput for TPMC. For hardware efficiency, I use IOstat and VMstat. In this case, kilobytes read per transaction, which is the second column. Myrox is slightly better than InnoDB. So InnoDB is using more storage for reads. From IOstat, the kilobytes written per transaction, InnoDB is using significantly more, writing more data per transaction back to storage. So write efficiency is worse with InnoDB. For CPU efficiency, I used CPU utilization from VMstat. Myrox is slightly worse. It's not surprising. In this case, Myrox is also spending time using zlib for compression. Next year, we hope to use zstandard, which is open source out of Facebook. zlib-like compression rates, but much less CPU latency. For the size, InnoDB was almost 3 times larger. So space efficiency is much worse with InnoDB, and this is what I like to see. I'm not happy that the quality of service, the 99th percentile response time, was worse for Myrox, but I did not have time to debug that. But again, peak performance or even average performance for me it gets too much attention. We care about performance with efficiency at scale. We tend to focus on getting good enough response time, good enough throughput, and then optimizing for efficiency, reducing the hardware required to serve a workload. For several years, we've had a few teams working on pursuit of better write and space efficiency. Out of this work came a paper published. I was co-author on the paper. The researchers are from Harvard on the RUM conjecture. RUM, or R-U-M, stands for read, update, and memory. At work, we've been discussing this for more years before the paper arrived, and we use RWS for read, write, and space. The conjecture is that one database algorithm cannot be optimal for all of read, write, and space amplification. So there is not one optimal database engine, at least not today. There is a need for a B tree and an LSM tree. This is a conjecture. It's not proven. It's not CAP, which has a proof. For now, it fits what I see in production and what I see in terms of hand-waving about performance. So it's about read, write, and space amplification, but I also use efficiency to mean the same thing as amplification. These are related to, but they're not the same thing as performance. So you can have better efficiency without necessarily having better performance. We use this internally because initially we had some discussions when RocksDB started that were too focused on performance. RocksDB can drive 300,000 page reads per second from storage. InnoDB can drive 150,000, so RocksDB is 2 times better than InnoDB. It's kind of a meaningless result because we don't run in production we don't try to do 150,000 page reads per second today. We'd run out of CPU. Generally, we're decompressing on every page read, and we don't have enough CPU to decompress at that rate. So I wanted to help the teams avoid getting stuck on faster is better and get them to consider efficiency and also the trade-offs we make to get better performance. So optimal, I said that the RUM conjecture, one algorithm cannot be optimal. So for any useful database algorithm, there always exists another algorithm that is better at least one of read, write, or space efficiency, or amplification. So for amplification, what I mean, or efficiency, it's a ratio. For read and write amplification, it's the ratio of physical work per logical request, or physical work per logical operation. And I will explain physical work and logical operation in another slide. For space amplification, it's the size of the database files over the size of the data. The size of the database files is easy to measure. You can just run, look at the files on the server. The size of the data in the database is harder to measure. That might require a table scan, and you also have to figure out how to account for secondary indexes, whether or not to include the benefit from compression. But so it's not always easily measured, but it's something to consider. So amplification is work per operation. What do we mean by work? It depends on whether we're considering storage or CPU. For storage, and especially for spinning disk, random operations are a key metric because you're likely to run out of random operations throughput before anything else. But bytes read from the device and bytes written to the device are also useful metrics. For CPU, we can think of high-level metrics such as the number of blocks uncompressed and compressed, the number of memory or cache operations. If we have a hash structure, we might consider the number of hash searches. For a tree structure, the number of key comparisons. The problem with all of these high-level metrics is that they're frequently not measured or not reported from the database engine. So, and it would be nice if we could collect these metrics and expose them, but unless you're willing to modify, which we are at Facebook, if you don't hack on the database engine, you might not see these numbers. So what I end up using frequently is just the number of CPU seconds. How much CPU is used as a proxy for these higher level operations. So for operations, while I would like to think of, so amplification is work per operation, I would like to use basic operations. And the basic operations I think of are point, read, range read, put, and delete. And the interesting thing here is that the basic operations described here match the low-level API that RocksDB provides. So if we think about an SQL update, explained on the right-hand side, if I'm skipping SQL semantics, I can just do a pure write for an update and not return a modified row count. But in practice, and to match SQL semantics, an update is going to start with a read and then possibly be followed by a write or even a delete and then a write. In practice, when I'm doing the benchmark evaluation, I use complex operations. So I could use queries per second, SQL statements per second, or transactions per second. And the reason I do that is that's what the benchmark clients provide. So going through, amplification is work per operation. This is the data that I provided earlier. How of that size of the page to the size of the row is the worst case for write amplification. Now, within ODB, it actually can be 2 times worse than this ratio because to protect against partial page writes, InnoDB uses something called the double write buffer, meaning we're doing twice the amount of I/O to do write back for pages. And so the real big difference for write amplification is B-tree writes back pages, LSM writes back and then rewrites rows. For space amplification, a B-tree subject to random updates will become about 2/3 full over time from fragmentation. So 1/3 of the space in storage and in the block cache will be wasted. So space amplification is about 1.5x, meaning if you took a fragmented B tree, compared it to the size of a fully defragmented B tree, it's about 1.5x larger. This is really for InnoDB. There are some modern copy on write B trees coming on the market, WiredTiger and LMDB, and I'm not able to discuss them here, but afterwards I can. Leveled compaction with an LSM tree, using RocksDB and Cassandra as examples. Reads are likely to have more CPU overhead. If you think of an LSM tree with leveled compaction as being a sequence of B trees in decreasing size, so the max level of the LSM would have n keys. The next level above it would have n over 10 keys. Above that, n over 100 keys. So the number of key comparisons to search all of these trees would be log n over 10, log n over 100. You can, for now, I'll just round that up and claim that that's 2 times log n, but someone can do the math. The problem is, in practice, we're using Bloom filters with the LSM tree. And Bloom filters help us avoid some of these key comparisons. And with RocksDB, we can even use prefix Bloom filters for some range queries, if the range query includes a equality predicate on the prefix of the key. So the read amplification is harder to predict because of the Bloom filter effect. Write amplification. So the key with LSM trees is we write the row when it's dirty, and then compaction is rewriting rows as they move down the tree. In practice, the write amplification that we're seeing, the number of kilobytes written to storage over time for a given workload is much less than we see with a B tree. So this is better than a B tree for write efficiency. It's going to be worse than a size-tiered compaction LSM tree. Space amplification is, I'm not aware of another file structure that allows for updates that is more efficient in space than leveled compaction LSM tree. Assuming 90% of the data is in the max level of the tree, 10% of the data is above the max level, you can then say that in the worst case, the 10% above the max level is duplicate with the data in the max level of the tree. Space amplification is about 1.1x, and this is what we see in production. So the B tree is 1.5x in terms of the hand-waving theory. This is much better. Just another reason we use less space. Size-tiered LSM tree. RocksDB supports this. We don't have many users of it. Cassandra and HBase, I would claim, are also size-tiered. Read amplification will be worse than what you see with a leveled LSM tree. Point reads can still use a Bloom filter, and some range queries can. Write amplification will be better than what we see with leveled compaction. However, the cost of being better is that space amplification is much worse than leveled LSM tree, and this is the reason that we don't use it, at least for the user database migration. In summary, the key point is that if you care most, depending on which you care most about, read, write, or space efficiency, you're going to choose a different engine. If you want the best read efficiency, you're likely to choose a B tree. If you want the best space efficiency, you're likely to choose leveled LSM tree, and best write efficiency, size-tiered LSM tree. So this is definitely not a proof, but just something that informs the RUM conjecture, that one algorithm is not going to be best at all of read, write, and space efficiency. Now, hand-waving theory is useful because when you're doing performance debugging, you have to construct theories, hypotheses, that explain performance, and then you go and collect the data to see if what's occurring in practice matches what you predicted. So these performance models are relevant, but they're not sufficient. I/O costs, how much storage will a workload use in terms of space, read, and writes is difficult for a couple of reasons. One is that access distributions in production have skew, and algorithms benefit differently from skew. And by skew, I mean some keys are more likely to be written and read than other keys. If we think about the like count for a celebrity, that row, if there is one row tracking the like count on a social network application, is going to be modified quickly. Likes for my posts are not getting modifications that quickly. The other challenge is that what's the benefit from cache? Now, if your working set is in cache, then great. You're not going to do many disk reads, and all you have to do is figure out how frequently you're doing write back. But if you have fast storage, then it's better to not have the working set in RAM. And so it can be difficult to predict the cache benefit for production workloads. One example of a production workload I care about, this is Linkbench. Linkbench is an open source synthetic benchmark modeled on the Facebook production workload on the user database tier from a few years back. So we had a research intern, spent about 6 months measuring the production workload, including key patterns of distribution and size, and this is implemented in Java. We still frequently run it for myrox versus InnoDB comparisons. Here I'm comparing myrox with zlib compression, InnoDB without compression, and InnoDB with zlib compression. The summary is that myrox has the best throughput, the best quality of service, and the most efficient. I'm happy. This is the workload I care a lot about. Hopefully, we can repeat this on workloads other people care about. The first is throughput in transactions per second. myrox beats compressed and uncompressed InnoDB. If we look at the reads per transaction measured from IOstat, they're about the same between myrox, InnoDB, and with and without compression. No big deal. myrox is actually matching, from a storage perspective, is matching the B tree on read efficiency, which is something I frequently see in my performance work. The big difference is write efficiency. So kilobytes written to SSD per transaction, measured from IOstat, InnoDB is almost 15 to 20 times worse, meaning it's going to wear out storage 15 to 20 times faster. This is a significant result. We didn't expect this to be the difference to be so large, and this is measured from IOstat. If I also include the writes that are done internally by the SSD to clean erase blocks so that they can be rewritten, the gap grows because the I/O pattern for myrox is more flash-friendly than InnoDB. So I think the gap might have been 20 to 25 times what myrox was writing once I included GC firmware from Flash. CPU load between myrox and InnoDB is about the same. And so myrox is almost matching uncompressed InnoDB despite having the additional cost from zlib compression. Space, myrox is almost 4x smaller than uncompressed InnoDB and about 2x smaller than compressed InnoDB. Now, can you compress your database tier in half or by 4? If you have a lot of data, it's a big deal. And so we're very excited about this result. And then the last one, the quality of service metric, the 99th percentile response time for the most frequent update transaction, myrox is significantly smaller. And here, smaller response time is better. The problem is you get jitter from InnoDB in write-back. And even, well, I didn't test it with Percona server. Percona, one of their claims to fame has been to reduce jitter in InnoDB. This is from upstream InnoDB. But page write-back is a hard problem to make jitter-free for a B tree. So why did RocksDB beat a B tree? This, for space and write efficiency, these are significant improvements over the B tree. The reasons for being better on space efficiency, first, fragmentation, B tree fragmentation. you are wasting space on storage and in the block cache with essentially by storing pages that are 1/2 to 2/3 full. The second is for compressed InnoDB, the fixed page size. So with compressed InnoDB, in this case, the in-memory page size was 16 kilobytes. The disk page size was 8 kilobytes. When a page is to be written back, if 16 kilobytes is compressed to 5 kilobytes, we still use 8 kilobytes on disk. So there's a roundup that essentially is throwing away some compression improvements. InnoDB has more per row metadata. So the per row metadata is 13 bytes. It includes a rollback pointer and a transaction ID. These are essentially random numbers. InnoDB with compression doesn't even try to compress them because they are random numbers. For small rows, 13 bytes overhead is significant. MyRox, the RoxDB, the metadata overhead is 6 bytes, the sequence number. And for the majority of the data, probably 90%, we compress that to 0 bytes. So less metadata. And then finally, there's no prefix encoding for keys with InnoDB. We benefit from prefix encoding for compressed and uncompressed pages for RoxDB. So that's space efficiency. Why does MyRox or RoxDB win on write efficiency? Well, the obvious one is if you use more space, InnoDB is less space efficient. You have more data to write back. The next reason is the way we configure the database servers. The working set doesn't fit in RAM. We have fast storage. We want to take advantage of it. So the B tree is writing back dirty pages too soon. And so in the worst case, the write amplification is the size of the page, 8 kilobytes or 16 kilobytes, versus the size of the row, which might be 100 or 200 bytes. And the final is the double write buffer. Most people run InnoDB with a double write buffer to protect against partial page writes on panic. That doubles the amount of writing that you do to storage. Here's an experiment I did to understand the impact of page size for InnoDB on write amplification. And so the base case is MyRox with zlib compression. Again, MyRox has the best transactions per second rate. InnoDB transactions per second, the second column, improves as you go from the largest page on the bottom up to a smaller page. Using a smaller page size, in this case, helped InnoDB. The most interesting result is the kilobytes written to storage per transaction. The theory or the speculation was large page size is bad for write amplification. And we can see here, the write amplification almost decreases linearly with page size. So great, use a small page for InnoDB, problem not as bad. Well, the problem with InnoDB is that your row needs to fit in half a page. So if you want to store some rows that are 8 kilobytes, almost 8 kilobytes, you need to use a 16 kilobyte page size. So it's very hard for many existing applications that want to support multi-kilobyte rows. They're not going to work with InnoDB in a 4 kilobyte page. But it did confirm my speculation that the page size has a significant impact on write amplification. So read efficiency. In some cases, we see better throughput with MyRox for read-heavy workloads. And the reason is that performance is complex. If you just look at an LSM tree on paper, you might say, oh, it's going to do more work, it has to check for data in more places, queries will be slower. But there's a lot more going on here. The advantage for the B tree, fewer key comparisons on searches. And in theory, less I/O for range queries. And link bench and the user database tier workload is very range query heavy. The advantage for the LSM tree, it uses less space. So even for uncompressed pages, which means it fits more data in cache, the cache hit rate is better. You're going to need to read less from disk per query or per transaction. Prefix key encoding is applied even for uncompressed blocks, so you're fitting more data in the block cache. the pages in the block cache are not fragmented, so you're not wasting space in RAM. Another point is that being more efficient on writes will save more I/O for reads. Now, the LSM algorithm was invented in the 90s, and it was designed for disk arrays. One of the ideas was that for the LSM tree is that being more efficient on writes, using less random I/O, allows you to do more writes per second on disks, or using less write I/O means that you have more I/O capacity reserved for reads. So the LSM tree designed for disks just I don't know if it was on purpose, it turns out to be a great fit for SSD. Better compression means you use less SSD. Better write efficiency means it lasts longer, and you save more I/O capacity for reads. Also with MyROX, non-unique secondary index maintenance is read-free. So with a B tree, on an update, if you need to maintain the secondary index, you're going to read the leaf page, modify it in the block cache, and eventually it gets written back. So there's maintenance is a delete followed by a put, and both of those are just write-only operations into the maintenance is a delete followed by a put, and both of those are just write-only operations into the mem table that RocksDB uses. So there's no disk read being done for that. For unique indexes, including primary keys, we need to do a read to confirm that we're not violating uniqueness. And then we have the Bloom filter. So many years ago, Damas Matuzis, some of you might know him from the MySQL community, figured out that we were about 30% of the disk reads we were doing on the user database tier was for keys that don't exist. We have a very effective cache called tau, and we also have memcache above MySQL. So MySQL, the reads that reach MySQL tend to be for colder data. Well, keys that don't exist are the coldest data. And so the cache tier was asking us to search for keys that don't exist, we have to do disk I/O, a large number. If we had a Bloom filter at the time, most of that would not have been done because the Bloom filter allows you to skip a lot of the disk reads. And here's another result to reinforce the idea that being more efficient on writes saves you more capacity for reads. This is the same workload running on MyROX and InnoDB. It's I/O bound. The database server has 50 gigabytes of RAM. 1,000 disk reads per second. The interesting thing here again is the absolute numbers don't mean much, but what is interesting is the ratio between MyROX and InnoDB when you move from fast storage to slower storage. MyROX is significantly better than InnoDB on the slowest storage because it's more efficient with random I/O. The difference between them is not as large on the faster storage. So again, that's my experiments to confirm some of the speculation I've done about why MyROX is doing much better than InnoDB. Some of the things we do, either between in choosing an algorithm or in tuning an algorithm, or even in managing our database servers, we're choosing between read, write, and space efficiency. So a standard way to trade between read and write efficiency is to create an index. An index costs in write efficiency because you have to write it to maintain it after updates, but it makes reads faster. An index also costs in space efficiency because you have to store the index while making reads faster. Compression is another trade-off between read and space efficiency. Compression makes reads slower because you have to decompress pages after reading them from storage. This is another reason why I'm very excited about Z standard. Decompression latency with Z standard is much better than zlib. So we want to continue using the compression rate we get from zlib with much less latency. And Z standard is the way to make that happen. The interesting result, so there's many ways to trade between write and space efficiency. Garbage collection frequency and defragmentation frequency is one common way. And in this case, I'm predicting worst case space and write amplification that we would see with the garbage collection done by SSD to make erase blocks clean to be rewritten. And so if you think about formatting a file system on an SSD device, usually you're able to choose how much space you make available to the file system. You might, and in some cases the vendor in the background also makes additional space available, and we call this over-provisioning. So let's say we have a 1 terabyte storage device. If you format a file system to use 512 gigabytes, then the percent full of the device is 50. You're using half the device. Space amplification, in that case, is 2. You're using twice as much physical space to store your logical space. So if we look at the graph on the right-hand side, when space amplification is 2, write amplification is also 2. The cost of doing the garbage collection that the firmware is going to do on the flash device is a factor of 2, assuming worst case behavior. Now the benefit from wasting space is you're reducing write amplification from the flash garbage collection. Your device endurance will last longer. But let's say that we want to use more space. So if we increase percent full to 90, so we're using 900 gigabytes now of the terabyte device, we have a lot more space available to the file system. The cost of that is additional write amplification during flash garbage collection. Write amplification is going to increase to a factor of 10. So to make almost twice as much space available on the device, we're now increasing the cost of garbage collection by 5x. So this is just one more example where we are trading between write and space amplification. So I think there's a few things that are coming, at least from what I work on. One is that one size doesn't fit all. So for some, I would like to see, if nothing else, a database engine with a B tree and an LSM tree sharing one redo log. Because I might want, we have many indexes in a workload, many tables. I might want different optimizations. I might want to optimize one index for space efficiency, another for write efficiency, and another for read efficiency. We don't really have that today, or we don't have it today. The next step beyond that would be adaptive algorithms. I would like the DBA to be able to set high-level goals for read, write, and space efficiency, and have the cleverness in the database algorithm pursue those goals to do the tuning. Tuning RocksDB is challenging today. So this is one way that we can make it easier. The algorithm needs to be adaptive, and this is one space where early research is in progress, but it's going to take some time to get there. The final thing is more open source. MyRocks is coming to MariaDB server and Percona server. I think that's going to happen in what would be called a beta next year. I'm really excited about that. I'm able to spend time helping it be successful, so I'm happy to it be successful, so I'm happy to speak with people. Certainly, I'm most interested in web scale users as early evaluators because they frequently have the resources, so please come speak with me. MongoRocks is in Percona server. I continue to spend time on it, if nothing else, doing performance evaluation. It's still better than WireTiger, significantly better for some workloads, especially write-heavy workloads. And then finally, we have a lot more work coming to RocksDB that we need to make available in MyRocks. There's a lot of innovation in RocksDB currently and planned that we need to expose to higher level users. And then there's two of us, Gunnar and myself, Gunnar is here, who do performance evaluation. Most of my work, I do performance work part-time. We have a lot of benchmarks that we want to understand. We want to explain how RocksDB is better or worse on these performance tests. And that takes a lot of time, and fortunately we have the hardware and the time to do that. So there's a lot of resources if you want to follow this work. There's a landing page for RocksDB and for MongoRocks. We're working on something similar for MyRocks. Right now we have a GitHub page for the Facebook MySQL branch, which includes content on MyRocks. I have a blog, Small Datum. I'm a small data engineer. I don't do big data. So that's where I write a lot. And then I tweet. So I'm on Twitter. And I welcome hearing from people who discover that MyRocks is working for them or not. We're willing to help understand what's going on. So thank you.
Thank you for your speech, and I have some special case for you. For example, we have an application with high write throughput, massive write, and we have some reads every hour. And what you can recommend use for this case, Cassandra or RocksDB or something, another solution for this case?
So for high write throughput, we have a lot of internal usage and usage at other companies of pure RocksDB. For cases where reads are infrequent, one of the things that RocksDB has is something called the merge operator, which lets you, let's say, do commutative operations. So the write can be logically an update that doesn't require a read. And then the read in the future would potentially have to gather deltas from multiple locations of the tree to compute the read result. So if you wanted extremely high write throughput, pure RocksDB, potentially with a merge operator, is a good way to get that.
Okay, thank you for answer.
Is Sergey Petrunia here? Oh, there he is, okay. Oh, now you have to ask a question, Sergey. What's it like working with Mark? You can ask a question. So this is Sergey Petrunia, who helps us a lot with MyRocks, and I'd like to acknowledge, I appreciate what he's doing to help make MyRocks better. So thank you.
My pleasure. I'm also working on putting MyRocks into MariaDB, so MariaRocks is coming. I can't give a date, but it will be there. MyRocks will be in MariaDB.
Thank you.
Hello, thank you for this talk. I just want to ask, have you compared this with DocuDB?
Yes. So I have friends, and my brother used to work at TokuDB, so I've been reluctant to share the performance results. I will begin sharing them. In almost every case, MyRocks does significantly better than TokuDB on disk arrays and on SSD. One problem that TokuDB has is with concurrency. The way that they do compaction down their tree tends to, at least what I've been told and what I see in performance, there are write locks taken on the tree whenever they're doing compaction from a node down to its child nodes, which means the reads are stuck briefly when compaction is moving data down the tree. So it struggles with concurrency. Myrox does much, much better with concurrency. And we have a large team now dedicated to Myrox. But I'm hesitant. I think TokuDB really should be the one to talk about where TokuDB is going. Just in the evaluations I've done, it's been worse in almost every performance test.
Okay, thank you.
In all your comparison, you use zlib algorithm. Do you compare other algorithms, for example, Snappy or LZ4?
So I have, well, this year I've been spending most of my time doing the performance evaluation. I do have, for Myrox with leveled compaction, I tend to use no compression for levels 0, 1, and 2 of the tree. LZ4 for the intermediate levels, like level 3 and level 4, and then the max level, I would use zlib or zstandard. That's costing me in throughput. So I have performance results I can share showing where if I used Snappy for the max level, I'll get better throughput than from using zlib for the max level because of the compression and decompression latency. However, the question then is, are you willing to use more space, because Snappy will use more space, to get better throughput? And so now it's a question of what do I value more? When I value better compression, I use zlib on the bottom. When I value better throughput, I would use Snappy. But different people will value that trade-off differently.
Thanks.
Давайте поблагодарим Марка за его отличную презентацию.
Let's thank Mark for this outstanding speech, and we continue in 3 minutes.